Now, hello students. Now we are going to discuss magnetic field at any point on the axis of current carrying circular loop. In last lecture, we discussed if it is a current carrying coil carrying current I and radius is R, the magnetic field at its center B equal to mu naught upon 4 pi 2 pi I upon R. Okay, so this is the formula for magnetic field at the center of current carrying coil. Okay, now we are going to discuss magnetic field at its axis. So for that purpose we need to make a diagram. So first draw a diagram. So this one is a current carrying circular loop. It is placed on the YZ plane. It is placed on the YZ plane. Look here, this is the x-axis, y-axis, and this one is the z-axis. This pen is the z-axis. So the loop is placed like this. Loop is placed like this on the YZ plane, okay, and this one is the axis, x-axis. Point P is here. Point P is here. This is the point P. The tip point is P, and we need to find the magnetic field at this point. Suppose that this is the point P, where you need to find the magnetic field. The current is flowing like this in this direction. The current is in this direction. If anybody this side, he or she will observe the current direction is the anti-clockwise. From my side, it will be clockwise. From this side, it will be anti-clockwise. So the loop is placed like this. We need to find the magnetic field at this point P, whose distance is x, and the radius of the loop is r, and the current in the coil is I. So for that purpose, we choose a small element, current element, ideal, because we need to apply the Biot-Savart law. So first we recapitulate what is the general expression for the Biot-Savart law. So Biot-Savart law told that the magnetic field at any point P, because of this small element ideal at any point whose distance is r and making angle theta, dB equal to mu naught upon 4 pi ideal sin theta upon r square. Children, everything is clear. Mu naught upon 4 pi is a constant whose value is 10 power minus 7. dl is the current element, dl is the length. Theta is the angle between radius vector and dl. Means this is the direction of dl, this is the direction of dl, and this is the theta. So theta is angle between dl and r. So the same rule is applied here. The magnetic field at this point P because of this element. So we join the element with the point P. This is r, capital R, this is x. So this is a small r is equal to x square plus r square. Okay, children. So the magnetic field at this point P will be by this formula dB equal to mu naught upon 4 pi ideal sin theta upon r. R means distance, means under root x square r square whole square. Now the question is theta. What is the value of theta? So for that purpose we need to find the theta. So look the diagram. This is your r and this is x. Compare this 2D structure with this 3D structure. This is the small x. This blue pen is a small x and this white pen is small r. So what is the theta? Basically theta is the angle between element and r, means joining line. So children, dl is here. This is dl. This is dl and this is the r. And it makes an angle how much? It makes an angle theta. Whatever the orientation, if you rotate like this, it always makes an angle theta. So the angle between dl and r is here how much? It is the 90 degree. So the theta is 90 degree. So what we get, children? dB is equal to mu naught upon 4 pi ideal x square plus r square. Whole square under root becomes cancel out. So sin 90 is 1. So simply you can write. Now assuming this is equation number 1. Now we know that the magnetic field is a vector quantity. So we need to find what is the direction of magnetic field at this point P. Okay. So let us discuss what is the magnetic field. So children, for the direction, we put our right hand thumb in the direction of current, and remaining finger towards the point where we need to find the magnetic field. Direction of magnetic field always perpendicular on your palm. So it will be inward, perpendicular to palm. That means this is your palm. It will be perpendicular. And here the direction of magnetic field will be outward, perpendicular to the palm. That means outward. So we apply the same rule here. Now look the 3D structure. This one is your ideal. This is ideal. Current is outward, ideal. Put your thumb in the direction of current, that means outward, and finger towards the point where we need to find the magnetic field. The point is here. So the direction of magnetic field will be perpendicular to your palm. That means perpendicular to this pen. Again say here, this is the direction of magnetic field, a current, point. So the direction of magnetic field perpendicular to the palm. That means perpendicular to this pen. So what is the direction of magnetic field at this point? It will be like this. dB, perpendicular to this. If I choose another element in just front of it, here, and join, because it is very symmetrical, so join the same distance R. So what is the direction of magnetic field because of this element? Look here. If the point is here, element is here, magnetic field perpendicular to the palm. If the point ideal is here, element is here, this is the point P, current is inward. Look here, current is inward. Put your thumb in the direction of current, finger towards the point. The direction of magnetic field is perpendicular to the pen. That means like this. So what is the direction of magnetic field? In this way. Now assume that this angle is alpha. So by symmetry this angle is also alpha. Now this one is your y-axis. This angle is alpha, children. This is perpendicular, so this will be 90 minus alpha. We already proved that this angle is 90. This is 90 minus alpha. So what about this one? Alpha. The same, by similarity, this is also alpha. So dB resolve in two components. dB cos alpha and dB sin alpha. The same thing is here. dB cos alpha, and this is the dB sin alpha. From the diagram it is very much clear. The dB cos alpha and this dB cos alpha are vertical and opposite. So therefore they will cancel. That means I can say whatever the location of element on the wire, on the ring, whatever the location of the element, all vertical components will, all dB cos alpha will cancel to each other. That means effective component is only dB sin alpha. So what is the net magnetic field at this point P? B will be integration of dB sin alpha. Now children, I will put the value of dB from equation 1. What we get? We get B equal to mu naught upon 4 pi I dl upon x square r square sin alpha. Okay. Now again, mu naught upon 4 pi I dl x square plus r square, and what is the value of sin alpha? It will be perpendicular upon hypotenuse. Perpendicular is r, hypotenuse is this one. So this will be r upon what? Under root x square plus r square. Now see this equation. Here all things is constant except dl. So all constant take the outside, and operator is dl. So your limit should be in the term of dl. So this will be 0 to 2 pi r for the whole circle. 0 to 2 pi r. So take the constant number outside. We will get B equal to mu naught upon 4 pi I constant, r constant, x square plus r square. Here power 1, here power 1 by 2. So it becomes 3 by 2. And dl from 0 to 2 pi r. Now integration of dl is L. When you put the limit, it will be 2 pi r. So what will answer? Mu naught upon 4 pi 2 pi I r square x square plus r square power 3 by 2. So this one is your final expression of the magnetic field at the axis point P. So you can simplify it, pi r square. Pi r square you can say the area. So you can convert pi r square into area. So this one is the final result, magnetic field at the axis point of a current carrying circular loop. Okay, now I can solve in the term of other components. So you can write here B equal to mu naught upon 4 pi r square is A, so 2ai upon x square plus r square power 3 by 2. Okay children, now if suppose that there are n number of turns on the loop, so you can multiply by n. For n turns, this formula becomes 2nia upon x square plus r square power 3 by 2. And there is another important physical quantity which we will introduce here. Nia is known as magnetic moment. So I can replace Nia, that is known as the magnetic moment, capital M. It is the magnetic moment. So you can write this formula, mu naught upon 4 pi 2m upon x square plus r square power 3 by 2. Okay, so this is the value of magnetic field at this point P. Now, what is the direction of M? Direction of M is similar to the direction of B. For finding the direction of magnetic field, look at the picture. This is the current. Direction of magnetic field is because of dB sin alpha, means all magnetic field is towards this direction, x-axis. This is the direction of current. So this is the direction of magnetic field. And this is also the direction of magnetic moment. So if anybody asks, what is the direction of magnetic field at this point? Along x-axis. And what is the direction of magnetic moment? It is also along the x-axis. So this one is your final result, by which you can calculate the magnetic field or magnetic field induction at any point on the axis. Thank you.